Okay, here we have a 3 reservoir problem, and we are asked to find the beta values and the discharges in each of these pipes. And we're given all the information in this table here. We're given the elevation of each reservoir, the length of the pipes, the diameter of each of the pipes, and the KS value for each of the pipes. I've also written the equation for the beta values right here. So yeah, let's get started. So we have, to start off this kind of problem, we're going to need to use the Moody diagram. And in order to use the Moody diagram, we need to figure out what Ks over D is. And since we're given Ks and we're given D in the table, we can calculate that for each one of these different pipes. So we have Ks over D for pipe A. We have 0.0020 over 1 foot. So the Ks over D value is just 0.002. For pipe B, we have 0.0005 over 0.75. And that is equal to 0.00067. And finally for C, we have 0.0001 over 0.75. And that gives us 0.00013. And now we have, see, these are our Ks over D values. So now we just read these on the Moody diagram, and we assume fully rough turbulent flow because it says to do that in the problem right here. So okay, for our A value for F, we have 0.002, which is right here. Change to red. We have that right here. So we just read this straight across. And we get, I'm going to say 0.023. So we get our FA is 0.023. And then we'll have one for B, and then we'll have an F value for C as well. So for B, we have 0.00067. So here's 0.006, so it's going to be a little bit above this line. So we'll pretty much just follow that straight across. And maybe a little bit above that line, right around here. So we'll say 0.0175. Or no, sorry, 0.018. Yeah, just 0.018, that's fine. For our C value, we have 0.00013, which is going to be somewhere in here. Just say it's right around here. And we go straight across, and we'll say that's about 0.0125 or 0.0126. Okay, so now we have our F values. Now we need to calculate our beta values. Since we have G, we know, D, we are given in the problem, we're given D, we're given L. There are no losses in this problem, it's being assumed. And now we've just calculated the F values. So, moving on, we have beta A is equal to, and we're just going to combine this and say 8 times F times L, which I'll just transfer in here, 0.023 times the length, which we're given in the problem is 500 feet, over pi squared times G, which is 32.2, times D to the fourth, and D in this, in part A is just 1 foot, so it's just 1 to the fourth, or just 1. And we will get this value to be 0.296. That's our beta value for A. And then we'll do the same for B and the same for C similarly. So we have 8 times the F value, which is 0.018, which we read from the Moody diagram. The length of this pipe is 225 feet. We still have our pi squared G on the bottom, times the diameter, which this time is 0.75 feet, and that's to the fourth. And we get our beta value as 0.437. And finally, beta C, same thing, just plug our numbers in. there needs to be another 0 in there. Our length of the pipe in this part is 350 feet. We have our pi squared g times the diameter, which didn't change from part B, which is 0.75 to the fourth, and we get a beta value of 0.468. So now that we have our beta values, this is where this problem differs from any of the other types of problems that we've done so far. So now we're trying to figure out, like, okay, we know that the flow is going to be going in or out of A into some of these, and then we also know that it's going to be going into C, but we don't know if it's going to be going into B or out of B. And that's where we're going to have to make some assumptions and test those assumptions out. So we're going to assume that the hydraulic grade line at this point here in the middle, which is point J, is right here. Well, not right there, I guess. It's right here at 80 feet. And that's probably your best starting point for any of these types of problems, is you're just going to want to assume that the hydraulic grade line at J is equal to the elevation in the middle reservoir that we're trying to figure out if it's going in or out of. So we will label this one, the hydraulic grade line at J is equal to 80 feet. That's this test that we're running here. So we have our Q's is equal to the head loss over, and that's from A to J, over our beta value for A. And that's going to be, so our elevation from A to 80 is 20 feet, which is 100 minus 80. And then our beta value for A we calculated right here to be 0.296. And we get our discharge of A as being 8.21 CFS. And then we can do the discharge at B, but the head loss is going to be 0 over beta B. So that's just going to be 0. So we can usually just neglect that for our first trial. And then for C, we have a head loss of -10, but it's just, in these types of problems, we only need to know the difference in elevation, not necessarily if it's going up or down. So we have just +10 over beta C, which is 0.468, and we get a discharge of 4.62, and we know that this is going to be negative simply because it's going out of J and into C. Just intuitively from the problem, we know that the flow is going to be going this way. So if we now how we figure out if this assumed hydraulic grade line at J is correct is we add all three of these values up here, and we get our delta Q. And in this case, we're going to have a delta Q of plus 3.6 CFS. So that's not very close to 0, because we want to satisfy continuity, which means all of the water coming into this point J has to equal all the water going out. So we now need to test a different hydraulic grade line at J, and we'll just we'll try 82 this time. This is just pretty much guess and check, and then figure out if we were right or not. So we pretty much do the exact same thing, except we'll have QB this time. So we have our QA, so the difference in elevation is 18 this time. 100 to 82 is 18, and same beta value, which is 0.296. And we get a value of that is 7.80 CFS. We'll have a value for discharge at B now, because there's a 2 foot difference in elevation here, and then we have beta B to be 0.437, and then finally QC we'll have a 22 foot, or excuse me, yeah, okay, it's a 12 foot difference in elevation, and then 0.468 is our beta value. And for these, we're going to get 2.14, and that's negative CFS, and then negative 5.06 CFS. And if we add these all up, we will get a value for delta Q to be plus 0.60 CFS. And this is a heck of a lot closer than 3.6, so we know that we're going in the right direction. We know that we need to be above 80, not below 80. And for this, we can linear interpolate this. So we have 80 minus 82, or 82 minus 80, I guess, over 3.6 minus 0.6. So we get 2 over 3. And so that's approximately 2/3 above 82 here. So we'll try for our next value, 82.65. Linear interpolation helps a lot in this case because we know two values. We know the difference in our hydraulic grade line of those two values. So yeah, that's how you linear interpolate this and try to figure out, get a good idea of what values you want to use next. So we'll do our HGL at J is equal to 82.65 feet this time. And we'll get QA is the square root of 17.35 over 0.296. That's an A. B, we're going to have square root of 2.65 over 0.437. And finally at C, we'll have 12.65 over 0.468. The values for these, when you calculate them, is 7.66. That's a positive. This is minus 2.46, and this is minus 5.20. And when we add those up, we get, I think that's just equals 0. Yeah, okay, so this is like the perfect case. Usually you're going to get within like 0.005 or 0.005 or something like that, and that's good enough. Then you can just linear interpolate again, and then you don't have to show this work here. You can just say like, okay, I linear interpolated this and I came up with a value for this, and then you're done. So we know that the flow of A is out of A 7.66 CFS. These all are cubic feet per second. And then so we know that the flow into B is 2.46 and the flow into C is 5.20. And that's what these negative values stand for, is going into the point from J would be negative, and then going into J from the point would be positive. So A is always going to be, your highest one is always going to be a positive value because it's flowing out of A into J. And then we have B, we don't know, but if B flows out of B into J, then we have a positive value, or if it flows from J into B, then it's negative, and your bottom one is always going to be negative. A couple ways to make this more confusing would be to add a pump here, right here. Similarly, you could add a turbine here, up top. There are a couple examples in the problems that Dr. Parr's posted online that would give you a better idea of how to do those kind of problems. But yeah, hopefully this review for these type of problems helped, and yeah, good luck on your test tomorrow.